Hi there, my name is James Davis. I'm a professor at Purdue University, and today I'll tell you about using selective memoization to defeat regular expression denial of service, or ReDoS. ReDoS is a long-standing problem, and in this work we explore memoization as a solution. In the process, we introduce a new finite automaton model, develop algorithmic and runtime optimizations, show that our approach extends to non-clean features, and evaluate on a large-scale dataset. Regular expressions, or regexes, are a popular tool for string matching problems. Conceptually, they're a means of encoding a simple string language, like the strings that look like email addresses. They're widely used in practice, and they're not exactly regular. Some of the regex extensions offered in most programming languages go beyond what can be done with clean, regular regexes. According to empirical studies, software engineers commonly use regexes when they're processing untrusted, unstructured text. For some examples, here's a regex that matches email addresses, one for IPv4 internet addresses, and one for Windows usernames. At runtime, the responsibility for checking matches is delegated to an entity known as a regex engine. Every mainstream programming language has one. In their implementations, they take a regex pattern like this one, and they convert it to a construct similar to a non-deterministic finite automaton, or NFA. The regex engine then simulates the NFA on the candidate string to see if it can find a match. So here's an example on the string AAA. The regex engine has a choice here. Should it go up or down? Most regex engines use a backtracking search, so it'll try going up, and A matches, so far so good. B doesn't work, so we're going to have to head back and go down. This time we see the A again. We have two more A's to kill, so there's one. And you can eat another A and proceed. We declare success. It matched. So this is a depth-first backtracking search algorithm. When they see a choice, they write down the options, try one, and backtrack to the others later if the first choice didn't work out. This is straightforward to implement, but it introduces potentially problematic worst-case match performance. In other words, the regex engine may take a very long time to answer some match queries. Here's an example of a superlinear regex. This one has exponential worst-case behavior. Regex engines will construct something similar to this NFA, which has two loops because of this extra quantifier. The extra loop makes the NFA ambiguous. Every time the regex engine sees an A, it's not sure which loop to take. Each A gives it two choices to explore, and additional A's compounds the number of paths exponentially. And critically, all these paths are leading to the same place over and over again. So this means that under the input, a bunch of A's and an exclamation point, we'll have an exponential number of paths to explore in the number of A's, and the regex engine will try all of them to show that this input doesn't match the regex. Now the situation isn't this bad for all regexes. Unambiguous regexes have linear time behavior, some regexes are polytime, and a few are exponential time. But regardless of their worst-case behavior, most regexes run in linear time on typical inputs. It often takes a malicious input to trigger the worst-case behavior. That's why these slow regexes get used in practice. Let's think about the implications of these properties when regexes are used within the web stack. This diagram represents the typical parts of a web service, from the user through a web client, past a firewall, into business logic, through persistent storage, and back again. All these systems support a reasonably consistent regex language for input sanitization. Any path a legitimate client can use, an attacker can use as well. And in a Regex-based denial of service attack, the attacker triggers a regex's superlinear worst-case behavior in a location that will affect other clients, for example, poisoning an event loop or a worker pool. ReDoS can affect individual web services like Stack Overflow, and it can affect many services at once, when it impacts CDNs and middleware like Cloudflare. But these aren't one-off examples. Recent research has shown that ReDoS vulnerable regexes are common in major modules and major websites. What's frustrating about this class of attack is that in some sense it's beyond the responsibility of the application engineer. ReDoS attacks are exploiting a weakness in critical infrastructure, in the regex engines used in most programming languages. As I wrap up this part of my talk, I'd like to highlight two additional things about regex engines. First, most regex engines use backtracking and expose applications to ReDoS. And second, although there are some regex engines with linear time guarantees, there are subtleties between regex engine dialects that render translation a tenuous task. Variations on the ReDoS attack have existed since the 1980s, but ReDoS continues to be a problem. Alternative algorithms are well known, but not widely adopted. We conjecture that the cause is technical inertia. Regex engines are complex and divergent in their semantics, and maintainers are understandably risk-averse. Backwards incompatible changes could have far-reaching effects. Therefore, with these constraints in mind, we set out to identify a backwards compatible approach that would protect an existing backtracking engine against ReDoS with minimal modification. Our main results are space-time complexity trade-offs of memoization for regexes, extensions to non-regular regex features, and runtime storage optimizations. The general approach we'll consider is called memoization. It's been proposed in the past, but until now no one has explored how to make it cheap enough to be practical. Let me first explain how a full memoization approach works. We've got our input, and the regex engine will simulate the automaton on this input. So earlier I talked about how a backtracking search works. The regex engine will come along and explore every potentially feasible path through the automaton. We'll say take the inner loop a couple times, stay at vertex 1, the one with an A, and advance offsets through the string. And when we fail, we'll backtrack and end up at the same point again, vertex 1 offset 2, vertex 1 offset 3, and so on. You can see that we're retracing our steps along different paths. The NFA simulation is visiting the same vertices at the same offsets over and over again. And that makes sense when you look at the definition of ambiguity. Ambiguity means there are multiple paths through the automaton that lead to the exact same place. So a natural solution to avoiding this redundancy is applying memoization. We'll introduce breadcrumbs into the NFA simulation, and if we see a breadcrumb, we know that path didn't work. So we can mark the vertex offset pairs as we visit them, and then short-circuit redundant search paths. So I've got an unsurprising theorem about this. If we memoize visits to every vertex, the simulation runs in linear steps for the input W, and it requires copying the input string for every vertex we memoize. Now this is a nice improvement in the time complexity, but these strings can be pretty long, so it would be nice to reduce the space complexity as well. The problem is that many real-world regexes are complex, with tens, hundreds, and even thousands of NFA vertices. Combined with long input strings, this space cost multiplier might be too much for practical purposes. Fortunately, we've shown that we can memoize visits to a selected subset of the vertices and obtain the same time guarantee with lower space cost. The first subset are the automaton vertices with integrity greater than 1, which result from quantifiers and disjunctions. These vertices can be reached along multiple paths. Since ambiguity means multiple paths, it makes sense that only memoizing these ones gets us the same effect. Same time complexity, lower space complexity. But remember, it's the compounding of paths through loops that's really problematic. If we just focus on those, we've shown that we can memoize still fewer vertices to trade a slightly larger but bounded time cost for even less space. Here we'll memoize only the ancestor nodes, the ones that are upstream from back edges in the automaton graph. Memoizing these doesn't prevent all ambiguity, but it does prevent compounding ambiguity. In the paper, we also extend our memoized non-deterministic automaton model to two common extended regex features, those with zero-width assertions, or lookarounds, and with back references. Our formalization followed Regex engine implementations, adding additional edge types into the automaton and considering the space, time, and memoization effects. So using selective memoization, we reduce the space cost without degrading the linear time guarantee. But nothing is free. We still have to pay a space cost, and we'd like to reduce that cost as much as possible. In the paper, we talk about different encoding schemes for the memo table, one of which seems quite promising. We evaluated our ideas in a prototype memoized regex engine, and we tested it on the largest existing regex dataset, which has about 500,000 regular expressions, of which about 50,000 are superlinear in the worst case. Our prototype supports 84% of this dataset, including 95% of the superlinear regexes. These figures illustrate the reduction in match times resulting from memoization on several examples. On the x-axis, we have the lengths of the input string. The y-axis is the match time in seconds in our prototype. In blue is without memoization, and in orange is with memoization. So here we have behavior on the exponential Microsoft username regex, the Cloudflare regex, a regex with lookaround assertions, and one with back references. Each figure illustrates the behavior predicted by our theorems for regular and extended regexes. In a larger experiment, we tested every supported superlinear regex with problematic inputs of different lengths, and our theorems correctly predicted the linear in the input length performance in each case. Now these time reductions are great, but we can't just move the cost from the time domain into the space domain. So we needed to check how practical our approach is in terms of space costs too. To start with, let's look at space complexity. The x-axis shows the vertex sets of interest for memoization, and the y-axis shows the sizes of those sets for each of the schemes. The whiskers are the first and 99th percentiles. The blue bars are all of the supported regexes, and the orange bars are the superlinear subset. So from this we can see first that full memoization would be costly, with an order of magnitude increase in storage cost over the original string. Remember, we have to multiply the number of vertices by the length of the string to see the actual storage cost. Second, we can see that the selection schemes will typically have a much smaller multiplier for both normal and superlinear regexes. But how do these complexities manifest as space costs during a realistic attack? Here we've got the space cost for evaluating each of the regexes in our data set using Stack Overflow sized input strings, about 20 kilobytes. The x-axis shows the memoization scheme. The y-axis shows the space cost. Note this is a log scale with a kilobyte, megabyte, and gigabyte markdown. The whiskers here show the 5th and 90th percentiles under 3 different encoding schemes: a full memo table, a hash table that only records positive entries, and run length encoding. So using the coarse metrics of a kilobyte is cheap, a megabyte is pricey, and a gigabyte is not going to work, our data show that in the orange bars, the hash table based encoding is simply not going to work out in any case. The overhead of hashing is just too great. In the blue bars, we see that a simple memo table starts out too expensive, but it reduces to pricey if we select carefully. And in the green bars, an efficient encoding scheme starts out pricey, but reduces to cheap with selection. In fact, combining selection and an efficient encoding scheme yields typically constant space costs in our experiments. Remember, the upper whisker there is a 90th percentile of costs. This concludes all the measurements I want to present. There's some more in the paper. The ReDoS problem has thus far defied a practical solution. In this paper, we revisited this problem from a data-driven perspective. Grounded in a new large-scale regex dataset, we explored 2 selective memoization schemes which have attractive time complexity guarantees and low space complexity. In experiments, our ReDoS defense achieves linear time behavior with constant space costs for 90% of superlinear regexes. So it seems that combining selective memoization with a good encoding scheme can eliminate ReDoS. In future work, we are examining bounds on the encoding scheme cost and working towards implementations in real-world regex engines. Thanks for your attention.